All right, so we're going to start with number 4 here. About the roller coaster, starting with a certain speed at the top of the hill, which is actually more realistic than 3, right? Because you rarely start with 0 speed at the top of the first hill of a roller coaster. And then we have an average force of friction, and in there they're telling you it's both air and friction with the track and wheels and such. And what speed will it reach at point 2? So, assuming that we've done number 3, kind of saw that, work is going to be done on the coaster by gravity, and in that it's going to change its position, which will change the amount of kinetic and potential energy it has by that work. All right. So, in number 4 here, though, one of the big things to realize is that friction does non-conservative work. So mechanical energy is not conserved in systems. Now remember, mechanical doesn't refer to like the machines, it refers to motion in general. So anytime we talk to the mechanical energy, there should have been an E in here. Anytime we're talking about mechanical energy, we're talking about all the different types of energy that have to do with motion or position or anything like that. But it's very good to note here that that's important, but that the energy of the system is conserved. So while the energy about motion isn't conserved because friction takes some of that motion energy and makes it into other forms like thermal energy, the overall energy of the system is conserved. And our system here would be the coaster, Earth, and the track, what I would say. It's always good to also show that you understand that potential energy gravitationally is about position, and that kinetic energy is about speed. So it's good to make sure that you let your reader know that you understand those concepts. So the fact that energy of the system is conserved is actually where we're going to start. That the energy at the top of the hill, which would be energy 1, is going to equal the amount of energy it has at the bottom of the hill, which I think is position 2. Right? Yep. The energy at the top of the hill is going to be the potential energy gravitationally, that's a G at the top, so that's 1, plus the kinetic energy it has at the top. And that's when it transfers, the equal sign you can almost think of it as work. When the work transfers that energy, it's going to transfer it to the gravitational potential energy at point 2, the kinetic energy it has at point 2, and the work that has to be done against friction, that non-conservative work. That work that takes some of that energy and converts it to forms not about motion, not mechanical energy. All right, so we got a decision to make. Where do you guys want to call 0 potential energy gravitational? What height do you want to call that? At height 2? Okay. So right at the bottom, right at that position 2, right at the bottom of that first hill, we're going to say the gravitational potential energy at that point is 0. Remember, 0 is always arbitrary. We can put it wherever we want. I think that's a great place to put it. We could have put it at the other place that you could have put it is the top of the first hill. You know, in this problem, those are the only two places in my mind that make sense. So now that we know where it is, we know that the potential energy gravitation at the bottom of the first hill, therefore, is 0. So at the top of the first hill, we're going to have the weight of the cart, and the height it's at, which would be height 1, plus 1/2 the inertia of the cart m, the speed of the cart at point 1. That's going to equal 1/2 the inertia of the cart, the speed of the cart at point 2, plus the work is done by the frictional force over d, and d is the length of track that the frictional force has been able to have this effect, done this work. So they tell us the frictional force is 1/3 the weight, right? Mine's 1/3. People have different things? It's one, okay. So my frictional force for me is going to be mg over 3. And my distance, I think, is like 50 meters, they tell me, or something. One reason they told me my frictional force in terms of the weight is so that, if you notice, I have an m in every term. So I can cancel it out. Because they're trying to reinforce the idea that on a roller coaster, the mass of the coaster and the mass of the people in it doesn't matter. The trip's the same whether or not there's anyone in the coaster. In the train is what it's, the train is actually what it's called. So now you have all your values. M's cancel out. You have G because the only planet that has roller coasters right now is Earth. They tell you H1. That's the height above our 0 point. They tell you V1. And I think they want you to find V2. Mass is in each term, so what can I do mathematically? Cancel it out. Yep. All right, let me know if you need help individually on this one. All right, folks, so I'm going to do number 2 about the high jumper. Well, it is spring track season, even though we still have, what, 2 feet of snow? At least. So, they kind of, in the question, they kind of lead you through this one. They're telling you the kinetic energy athlete is transformed into gravitational potential energy. And then they ask you, what speed, which would be related to the kinetic energy, to lift the center of mass this high and cross the bar, the speed of this. So, in this one, mechanical energy is conserved in the system. And the system would be the jumper and the Earth. You can always show that you understand that potential energy is about position, and the kinetic energy is about speed. And that's probably about all you really need. Because any work done on this system, because mechanical energy is conserved, it's just going to go into changing the form of the mechanical energy, not changing it. So, the energy at the launch is going to equal the energy over the bar. So at the launch, they're going to have kinetic energy and potential energy gravitationally. And over the bar, they're going to have kinetic energy and potential energy gravitationally. Call that bar and launch. Where do you want to say 0 gravitational potential energy is? Probably either at the launch or at the bar. I'd say at the launch. It's probably easier to think about. So this we're going to say is 0. So the kinetic energy they'll have at the launch is 1/2 the inertia times the velocity, the speed squared at the launch. Kinetic energy at the bar would be 1/2 m their speed at the bar plus, and the gravitational energy, potential energy over the bar would be mg their weight and the height over the bar. M cancels out, doesn't it? And I think they tell you the speed they go over the bar, right? 0.74 meters per second for me. They tell me the height of that bar, 2.2 meters, which is a pretty good jump there. So height, I have the height. I know it's on G because it's the only place that high jumps is the Earth. They tell me, and it's just plugging in now. That concept that mechanical energy is conserved in the system is the key concept here. Yep.